Good morning, sir. Myself, B. Anil Kumar from CSC A section. My topic is deadlock avoidance. Introduction to deadlock avoidance. Deadlock is a situation where two or more processes are unable to proceed because each is waiting for the other to release resources. Understanding deadlock avoidance is crucial for effective resources management in operating systems. This presentation will explore the concepts, strategies, and algorithms used in deadlock avoidance. First of all, we have to know what is a deadlock. A deadlock occurs where processes are stuck in waiting state indefinitely. It can lead to resource wastage and decreased system performance. Identifying and handling deadlock is crucial for the reliability of computing systems. Necessary condition for deadlock. Deadlock can occur only if four conditions are present: mutual execution, hold and wait, no preemption, and circular wait. Each process must hold at least one resource while waiting for additional resource. Understanding these conditions helps in developing strategies for deadlock avoidance. Four conditions for deadlock. Mutual execution condition. Each resource assigned to one process or is available. Hold and wait condition. In hold and wait condition, process holding resources can request additional. No permission condition. Previously granted resources can forcibly taken away. In no permission condition, previously granted resources are cannot forcibly taken away. Circular wait condition. In circular wait condition must be a circular chain of two or more processes. In circular wait condition, each is waiting for the resource held by next member of the chain. Deadlock avoidance and deadlock prevention. In deadlock avoidance aims to ensure that system never enter a deadlock state. In contrast, deadlock prevention seeks to eliminate one of the necessary conditions for deadlock. Both strategies can implement based on system requirements and resource allocation policies. Resource allocation graph. The resource allocation graph is a visual representation of the allocation of resource to process. It helps in detecting potential deadlock and understanding the system state. By analyzing this graph, system can make informed decision to avoid deadlocks. Banker's algorithm. The Banker's algorithm is a classical deadlock avoidance algorithm used in operating system. It assesses resource allocation requests and simulate resource allocation to determine if the system is in a safe state. In the allocation keep the system in a safe state. The request is granted, otherwise it is defined. Banker's algorithm. Banker's algorithm is a classical approach to detect avoidance the resource with the multiple. Assign a credit limit to each customer. Maximum claim must be state negotiated in advice. Reject any request that lead to dangerous state. The dangerous state is which sudden request by any customer for the full credit limit would lead to deadlock. The recurrence reduction procedure recognizes dangerous state. In practical, this means the system must keep resource use will be below capacity to maintain reserve sulfur plus. Safe and unsafe states. A safe state is one where the system can allocate resource without leading to a deadlock. An unsafe state wherever it is one where the system may enter deadlock situation if all requests are generated. The goals of deadlock avoidance is to maintain the system in a safe state. Deadlock handling. Avoidance safe unsafe state. A safe is a, a state is a safe is the system can allocate resources to each process in some order and still avoiding a deadlock. More formally, a system is a state only there exists safe sequence. If no safe requests exist, the state is set to unsafe. Avoiding circular wait. Circular wait is one of the necessary conditions for deadlock, and avoiding it can prevent deadlock. One strategy it is to impose the static ordering of resource type. The process or request to resource is predefined order, reduce the risk circular wait. Resource allocation strategies. Resource allocation strategies can significantly influence deadlock avoidance. These strategies include priority based allocation using timeouts for the resource request. Efficient resource allocation can help maintain system stability, avoiding deadlocks. Implementation challenges. Implementation deadlock avoid algorithm can be complex and resource intensive. System must constantly monitor resource allocation and process state. The overhead of these checks can lead to perform issue, especially in high loading environment. Real world examples of deadlocks. Deadlock can occur in various systems, including database network, protocol, and multi-threading applications. Practical example helps illustrate the importance of deadlock avoidance strategies. Understanding these real-world scenarios can aid in designing better system. In real-world example of deadlocks can occur in various systems, including database, network, protocol, and multi-threading applications. Particular examples helps illustrate the importance of deadlocks avoidance strategies. Understanding these real-world scenario can aid in designing better systems. Compression of deadlock avoidance algorithm. Different algorithms have varying efficient and resource requirements. Some algorithms like Banker's algorithm are more suitable for static resource allocation. Others like weight diet and own weight schemes are better suited for dynamic environments. Tools for deadlock detection. While this presentation focuses on avoidance, detection tools are also essential for the system health. These tools can identify deadlocks and provide recovery mechanism. They often work in conjunction with avoidance strategies to ensure system reliability. Into tools for deadlock detection. These tools can identify deadlocks and provide recovery mechanism. While while this prevention focus on avoidance, detection tools are also essential for the system health. They often work in conjunction with avoidance strategies to ensure system reliability. Future trends in deadlock avoidance. Avoidance in operating system design may lead to more efficient deadlock avoidance strategies. Mechanism learn and AI could offer new opportunities to predict and mitigate deadlock situation. Ongoing research aim to ensure system performance while minimize the risk of the deadlocks. Summary of key points. Deadlock avoidance is crucial for maintaining system performance and reliability. Understanding these conditions and implementing effective algorithm can prevent deadlock. Continuous monitoring and adapting strategies are essential for the modern operating systems. Thank you.